Time feels simple. It moves forward. Always has. Always will. We remember the past, but never the future. We age, decay, and evolve in one direction. But the deeper physics becomes, the stranger this assumption looks. Because most fundamental laws of the universe don't care which direction time moves. If the laws of physics work forward and backward, why does time seem to move only one way? Time feels obvious. It moves forward, from past to present to future. We remember what has happened. We anticipate what has not. We age, we grow, we decay. Everything unfolds in one direction. But this sense of direction is more mysterious than it first appears. Because at the deepest level of physics, most laws don't distinguish between past and future. If you took the equations that describe motion, gravity, or electromagnetism and reversed time, they would still work. Particles could retrace their paths. Forces would behave the same. Nothing in the equations forbids it. So why don't we see time running backward? Why don't shattered glass reassemble? Why don't smoke clouds gather back into flames? Why don't we remember tomorrow? The answer begins with entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. A tidy room has low entropy. There are only a few ways to keep everything organized. A messy room has high entropy. There are countless ways for things to be disordered. Over time, systems tend to move from order to disorder, not because it's required, but because it's statistically overwhelming. There are simply more ways for things to be messy than tidy. This tendency gives time its direction. As entropy increases, we experience time moving forward, not because time itself flows, but because disorder accumulates. We remember the past because it was more ordered. Records exist, structures remain, causes leave traces. The future, by contrast, has not yet formed these records. It exists as possibility, not memory. So, the arrow of time may not come from physics alone, but from thermodynamics, from probability, from statistics, from the simple fact that disorder is easier than order. But this explanation raises deeper questions. Why did the universe begin in such a low entropy state? Why was the early cosmos so ordered? Without that initial condition, time might not have an arrow at all. This is one of cosmology's deepest mysteries. We understand how entropy increases, but we don't fully understand why it started so low. Some suggest it's tied to cosmic expansion, others to quantum fluctuations, others still to boundary conditions we don't yet grasp. And here again, explanation reaches a limit. We can describe the arrow of time. We can model it. We can measure entropy increasing. But why the universe began ordered enough for time to have direction remains unresolved. There's another layer to the mystery, our experience of time. We feel time passing. We feel the present moment moving. Yet physics contains no now, no universal present, only relationships between events. In relativity, past and future coexist within spacetime. The distinction between them becomes observer-dependent. Time does not flow in the equations, only in our experience. So the arrow of time may be part physical and part psychological, shaped by entropy and by consciousness. Why does time only move forward? Because disorder increases, because records form, because memory works in one direction, because the universe began ordered enough for change to accumulate. But beyond these explanations, the deeper question remains. Why did the universe begin in a state that allowed time to have direction at all? We can trace the arrow of time, but we cannot yet explain its origin. And so, like existence, like laws, like mathematics, time leads us again to the edge of explanation.